Good morning, student. I am NV Krishna Rao, Assistant Professor in CSC Department. I am handling compiler design subject for the 5th semester. So, in the last classes, we have discussed the front end, back end, compilation process, compilers, and interpreters. Now, we'll discuss the phases of a compiler. So, in today's class, we'll discuss the phases of a compiler. We'll discuss what is the importance of each phase of a compiler for the construction of the compiler, right? So this is the diagram of the phases of a compiler. The first one, lexical analyzer. So the first one is lexical analyzer. Second one, syntax analyzer. Third one, semantic analyzer. Fourth one, intermediate code generation. Fifth one, code optimizer. Sixth one, code generator. So all these are the phases of a compiler which convert one form of the source program to another form of the source program. For in the conversion of source program to target program, right? The source program might be any high-level language program. The target program might be assembly language program or machine code program. So these 6 phases will convert the source program one form to another form to finally generate the target program. The first one is lexical analyzer. So first we'll discuss the diagram with importance of the each phases. So the first one is lexical analyzer. So here this is a first phase which takes the input of the source program. Here in general we write the source program, right, with comments. Every line will be followed by a comment for description of the purpose of the statement. Because in real world, someone will write the programs, someone will use the programs. So to understand the programs very easily, so there will be a description of the task of the statements in the source program, right? It might be there are 10 lines, there will be another 10 lines or 20 lines for the description of the task and statements. So the first task of the lexical analyzer, remove all the comments, remove all the blank spaces so that the size of source program is reduced. That is the first task of the lexical analyzer, right? The first task, remove all the comments and all the blank spaces so that the size of the input source program is reduced. The next task, read each character by character of the source program and construct the tokens with respect to the patterns prescribed by the programming language. A pattern is a rules, lexical rules are regular expressions which represent the programming language constructs. It might be identifiers, it might be operators, keywords, like that. So using that lexical rules called the patterns, using these patterns will group the character by character of the input source program to a group of tokens. The output of lexical analyzer is a sequence of tokens. The tokens, it might be identifiers, numbers, operators, right? So the output of the lexical analyzer is a sequence of tokens. Right? Next, the sequence of tokens will be the input to the syntax analyzer. Right? The output of lexical analyzer, the sequence of tokens, will be the input to the syntax analyzer. The main task of this syntax analyzer is construct syntax trees for the input sequence of tokens according to the syntax rules of the programming language. So what are the syntax rules of the programming language? In general, every statement should end with semicolon. If it is a binary operator, there should be two operands. If it is a uni operator, there should be one operand. If we are declaring the multiple variables, it is separated by comma. So here these are the different syntax rules of the programming language. So this syntax analyzer will follow the syntax rules of the programming language, and it will generate the syntax trees. It will generate the syntax trees. Right? So here the output syntax trees of the syntax analyzer will be the input to the semantic analyzer. The semantic analyzer will check the execution of the syntax trees. The syntax trees syntactically correct according to the programming language, but the execution status will be checked by this semantic analyzer. For example, mod operator should have an integer. If it has a float variable, it will generate the array message. Array index should be integer. If it has a float value, a double variable, then the semantic analyzer will generate the error message. So the semantic analyzer will check the execution of the statements. It properly executed or not. If any semantic errors occurring, it will generate the error messages. Then the abstract syntax trees, the output of semantic analyzer, will be the input to the intermediate code generator. Here, the intermediate code generator will have the intermediate code forms: 3 address code, abstract trees, postfix forms. So these are the different intermediate code forms. The semantic analyzer abstract output, the abstract syntax trees, will be converted to the intermediate code form 3 address code. So that is the output of the intermediate code generator. For example, we are considering 3 address code, right? One of the intermediate code forms that will be input to the code optimizer. This code optimizer is an optional phase, but its main task to make the intermediate code more efficient and take less space, so that execution will be faster and efficient. So that is the task of this code optimizer. It will optimize the 3 address code output of the intermediate code generator to be optimized with a different optimizing method, so that resultant code is efficient, executes faster, efficiently, right? Then this optimized 3-address code will be the input to the code generator. It will be the input to the code generator. This code generator will convert this intermediate representation to the target program. It might be assembly program or it might be machine level program, right? This code generator will convert this 3-address code, the optimized intermediate code form, to the final assembly language program or the machine level programming language. Here, symbol table and error handler are the two other phases which connect with each phase of the compiler. The information about all the variables, operators, keywords, its scope, and initial values, everything is maintained with the symbol table. If any error is generated by any phase of a compiler, that will be handled by error handler, and it will convert with suitable sentences understood by the user, so that the corrections will be taken care by easily, right? So the error handler will add a description for the error, a location, expected correction, so that the user can do the corrections very easily. So this is the structure block diagram of a compiler, right? So what we discussed, the first one is lexical analyzer. The lexical analyzer will also be represented as scanners. It will read the source code from left to right, character by character, and group them with the meaningful sequences called the lexemes. Here, lexemes are the similar group of characters. These lexemes are converted to tokens with additional information according to the patterns. The patterns is the lexical rules described by the programming language, right? So the lexical analyzer simply group the characters one by one to form the lexemes. Then it will construct them lexemes to tokens with additional information. For example, if a variable identify is there, right? So that identify is stored in symbol table. That record number will added along with this lexeme to make it a token, right? So the lexeme followed by symbol table entry description will result to a token. The output of lexical analyzer is a sequence of tokens, right? So this lexical analyzer will classify the lexemes into a group of tokens, a constants, a identifiers, a keywords, and it operators, and it stores them in different tables, and it will update the information by each phase of the compiler. So whatever the information that is stored in the symbol table is used by every phase and updated by every phase of a compiler. The most of the symbol table is filled by the lexical analyzer, and later it will be added or updated with additional information by the remaining phases of a compiler, right? So a token is a pair of token name and attribute value. The token name means the lexeme. Attribute value means the entry in the symbol table, right? So the output of lexical analyzer will have a pair of token name and attribute value, right? Lexeme is a sequence of characters in the source program that is matched by the pattern for a token. Is it clear? Lexeme is a sequence of characters that is matched by pattern for a token. What is a token? A sequence of characters. It is treated logically a single logical entity. It might be identifiers, it might be keywords, it might be operators, these special symbols are constant. Recognizing them, the rules are called as pattern. What is a pattern for identifiers? A letter followed by letter or digit is the pattern, a lexical rule for the identifiers, right? So will the programming language will have these lexical rules or patterns by which we group the lexemes into tokens, right? So that is the task of the lexical analyzer. So we have a equal to b plus 3 semicolon. That is the input to the lexical analyzer. What is the first character? A. Then the lexeme A would be mapped to tokens such as identifier 1. So the variable A is an identifier, that is the first entity. Then it is stored in the symbol table. The entry record number is 1. So we say as A is mapped to token ID comma 1. Right? So that identify A and its information is stored in the symbol table in the record of 1. First record. So here the lexeme A is associated with a token ID comma 1. What is the second character? Is assignment. It is an operator. Simply we represent it as operator. It will be stored in the operator table, right? That assignment operator, the lexeme assignment operator is mapped to the token, the assignment operator, right? Then another input character is B. Here it will be mapped with the identifier and it is stored in the secondary record of the symbol table, and the lexeme B is associated with the token ID comma 2, saying that this lexeme is an identifier and it is stored in the record number 2, right? Next one, plus sign is an operator. So we are refer the operator table and we construct the token with the operator sign. Then lexeme 3. It is a constant. It is a number. Simply we can represent as simply a number, or we can say number comma 3, right? Then semicolon. It is a operator. So we say as semicolon, right? These are the lexemes we are associating with respect to tokens. Then the input of the lexical analyzer is a sequence of characters and the output of the lexical analyzer is sequence of tokens. The first token is identifier. Second token assignment operator. Third token is identifier. Fourth token operator plus sign. Fourth token number 3. Fifth token semicolon. So the final output is a sequence of token, is the output of the lexical analyzer. We are considering another example. Position equal to initial plus rate into 60, right? That will be converted into a sequence of tokens. Identify 1, assignment operator. Identify 2, addition operator. Identify 3, multiplication operator. Then number 60. The sequence of character input is converted into a sequence of token as output of the lexical analyzer. So the position, assignment, initial plus rate into 60 is converted into id comma 1, first identify, assignment operator, second identify, plus operator, identify 3, multiplication operator, a constant 60. Okay. Then next one, syntax analyzer. This syntax analyzer also called as a parsing, right? Here it will construct a tree-like structure called the syntax trees or parse tree according to the syntax rules of the programming language. The output of the lexical analyzer is sequence of tokens. The sequence of tokens are grouped into a tree structure format called as lexical syntax trees or parse trees, right? According to the syntax rules of the programming language, right? So the remaining phases of a compiler will use this tree structure, parse trees, or syntax trees, and it will convert another forms of the source program to generate the final target program, right? This is an example for the syntax tree. id plus id into id. The sequence of characters, sequence of tokens, id, token, plus sign, identify, multiplication, and identify. id plus id into multiplication, right? So id plus id multiplication id. So here this expression will be converted into a syntax string, right? Or it will be called also a parse tree, right? It will follow the context-free grammars in which the syntax rules of the programming language are represented, right? So using that context-free grammar productions, the tokens are converted into syntax trees or parse trees by the syntax analyzer, right? That is a second phase of the compiler. The third one is semantic analyzer. It will check the syntax trees are executed properly or not. The meaning of the sentence is correct or not. Any conversions is required. It will perform the conversions of one data type to another data type, or any missing symbols are there, it has to add them so that the remaining phases of a compiler will process this one without any break. That is the task of this semantic analyzer. It will check it properly, it will be executed or not. If any necessary actions required, it will be taken care by this semantic analyzer to make the expression will be converted properly from one phase to another phase to generate the final machine language program, right? That is a task of the semantic analyzer. So any tab type mismatches, incompatible operands, a function called with improper arguments, or undeclared variables are the different examples of the semantic analyzer others are checkings, right? Collect other information needed by the backend analysis and code generation. It fills whatever the information required and it will pass to the backend and code generation phase to perform the conversion of source program to the target program. So type mismatch. If we are saying int assignment float value, so assignment operator is associated with integer operand and float operand. So that are incompatible. So it will perform the internal conversion, converting internal integer to float type. Then it will perform the float assignment, right? So this type of conversions will be done by semantic analyzer. Because if you are doing any assignment, that both operands should be of same type. If not, the semantic analyzer will take care of them and it will convert one data type to another data type and makes both of them equal data types and perform the respective assignment operation, right? We'll see. Here, float x equal to 20.2 means it's a float variable. Okay. Float y equal to x into 30. Y also float variable. Y is float variable. X is float variable. But what is a 30? It is an integer constant. It is an integer constant. So, the semantic analyzer will convert that integer to the float and perform float multiplication, later float assignment, right? Here, instead of generating the error messages and stopping the conversion of source language to target language, the semantic analyzer will take care and convert that integer to float. The task is taken care by semantic analyzer such that the conversion process will not be stopped. It will be continued to the next phases. Type checks are performed whenever is required, like array index as float. Array index always must be integer. If it is a float variable, it will be converted to integer. Otherwise, it will generate the error messages. The next phase is intermediate code generator. Here, it will have different intermediate forms, 3 address code, abstract syntax trees, postfix notation. The abstract syntax trees output of semantic analyzer will be converted to one of the intermediate code forms. It is a bridge between analysis phase and synthesis phase, right? It is a bridge between analysis phase and synthesis phase. It is easy to produce and easy to translate into target machine. It is simply an intermediate representation. The intermediate code generator will generate a intermediate representation into one of the 3 intermediate forms. Example is 3 address code. We'll see. So here total equal to count plus rate into 5. It will be converted to this 3 address code representation. Right? This is a 3 address code representation. T1, T2, T3 are the temporary variables are generated in for the execution of the statement. Total equal to count plus rate into 5 only. But it will divide the tasks and execute one by one. And finally, the result is stored in the total variable. Right? Is it clear? So, first task, into to float of the file. Here, 5 is converted to float type. Then because total, count, rate are the float types, 5 is integer type. So the semantic analyzer will perform the conversion of 5 to float, right? Integer to float. Then float multiplication taken care by rate into table. Then float addition will be taken between the count and T2. And finally, the resultant T3 is stored into the variable total. Right? So the single normal statement we are converting into 3 address code representation is a one of the intermediate representation. It is a bridge between analysis phase and synthesis phase. Then code optimizer. The code optimizer its task is to make the intermediate code more efficient by applying the optimizing methods such that it takes less space so that execution will be faster and also it will be efficient, right? So here already we have seen total equal to count plus 8 into 5 is converted into 3 address code. Now we'll see what this code optimizer will do. T1 equal to rate into 5.0, total equal to count plus T1. Here in this intermediate representation form, how many statements are there? There are 4 statements. But in optimized intermediate form, there are only 2 statements. The intermediate representation having 4 statements, right? If we consider further, there are 7 tasks, 7 expressions are there. Conversion of into to float, multiplication, addition, and 4 assignment operations. These are the total. There will be 7 operations. But the resultant optimized intermediate code having 2 assignment operators, 1 multiplication, and 1 addition. So the number of operations, the number of statements, both are reduced. It taking less space so that execution will be more faster. And it will not change the output. Output will not never change, but program become more efficient, right? That is a task of the code optimizer. One more example. So here, 3 address code having 3 statements. The 3 statements are converted into 2 statements. 3 assignments and 1 multiplication and 1 addition, right? There are 3 assignments, 1 multiplication, 1 addition. 5 operations, 3 statements. But resultant, it has 2 assignments, multiplication and addition. So number of statements, number of operations are reduced, but output will not be changed, right? That is the task of the code optimizer. Okay. Then the final phase of the code generator, right? The final phase is code generator, right? The optimized intermediate code will be converted to the a assembly language or machine level language programs. It uses the different machine instructions and it will convert the intermediate representation into machine code by using the machine instructions of the respective machine on which it is compiled, right? So the output of the code generator is the machine language of the given source program, right? This is the final phase of the compiler, right? It will convert the optimized intermediate code form into a machine language, on which machine it is executing the output, executing the machine code, right? So the two statements in the optimized intermediate code is converting to this 1, 2, 3, 4, 5 statements, right? This is the code generator. So in this class we're discussing the phases of a compiler. So I'm closing this section for today, and we'll continue with some more examples in the next class. Okay.
Like, share and subscribe. Hit the bell icon for more updates.